Alright, hey guys, this is James, one of the undergraduate tutors for C100A, and I'm going to be going over problem set number 11, question number 6. So let's read through the question first. It says, a researcher is trying to understand the mechanism behind catalysis for an enzyme and measures activity profiles as a function of pH. The researcher is particularly interested in probing the interaction between two amino acids, not amigo acids, K139 and D135. And tests the effect of mutating them to alanine. So let's talk about the notation real quick because that might throw some of you guys off, right? So when it says K139, what this means is that at position 139 of the amino acid or of the protein, there is a lysine, right? So when we have this notation K139A, what this means is at position 139, oops, did not mean to move that. At position 139, there's originally a lysine. However, it's been mutated to an alanine. So K refers to the original amino acid, 139 refers to the position, and A refers to the new mutation, so the new amino acid. So now that we've talked about that, let's go into the question. Which residue likely acts as a general acid base to promote catalysis? So when it's asking which residue acts to promote catalysis, it's asking which residue is the most important in catalysis. So if we look here, we see when we mutate K, there's still activity, right? However, when we mutate the aspartate at 135A or at 135 to alanine, we lose activity of the enzyme. So from there, we can assume that D135A is the critical catalyst. That's because there's a loss of function when you lose that amino acid. So the researchers also particularly intrigued by the K139A mutation at low pH, in which the mutant has higher activity than the wild type enzyme. Does this make sense to justify? So this is actually a question regarding pKa. So one thing we should note here is that for a residue that's acting as a general acid base to promote catalysis, it has an optimum. It usually has an optimal activity when pH is equal to pKa, and that's because at this pKa, 50% of the amino acids will be acids and 50% will be conjugate base. So that's the big thing we should note here, right? So let's think about the interaction of aspartate with lysine and how that affects the pK of aspartate. So let's call pKa not our original pH or pKa, right? And pKa, I'll put a K here for interaction with lysine for the pKa when D is with lysine. So this is by itself. This is by itself. And this is when D is with lysine. So let's think about it. So if we recall, acid dissociation constant is HA yields H plus A minus, right? So we know that the acid dissociation constant is thus equal to H plus times A minus over HA. And then from there we can get our formula for pKa, in which pKa is equal to negative log of Ka. So looking at this formula, we can see there's a relationship between Ka and pK, and that's that they're inversely proportional. So as Ka increases, we would expect pKa to decrease, right? Or pKa to decrease. So let's look over here now. So for pKa, which is when D is interacting with K plus, right? Since there's a positively charged amino acid that's stabilizing the negatively charged conjugate base of aspartate, right? We can say that lysine allows there to be an increase in concentration of the acid or of the conjugate base, and subsequently a decrease in the concentration of the acid. So therefore, from this interaction, we can say that the pKa K. So since so let me go back real quick. So from this interaction, we see that Ka increases, right? Because there's more A minuses and less HA, and therefore pKa should decrease. So from there, we can say that pKa should thus be less than the pKa of just aspartate by itself. So now let's relate that to the question. So it's asking to justify the change in pH, the change in activity in pH. So if we look here at the K139A mutation, right? So that's when you get rid of the K139 and you replace with an alanine. So from there, there's no more positive charge to stabilize the to stabilize the aspartate, right? So because of that, pKa increases, so it goes from pKk to pK naught, right? And subsequently, we see an increase in pH right here. So that's the reason why this graph makes sense. It's because when we're removing the K139A, it's removing the positive charge that's stabilizing the negatively charged aspartate, right? And because of that, we would expect our pKa to decrease. So or we would expect our pKa to increase because there's no more stabilizing force. So therefore, we see an increase in the optimum pH at which or the pH at which optimal activity is occurring. Hopefully this makes sense. If you guys have any more questions regarding this, let me know and I'll try to answer it. Alright, thanks for watching.